I'm going to be talking about eBPF and security and open source project called Tetragon. Since it's just you at this point, I shall ask you, have you got any experience of eBPF at this point? Okay.
I want to put your hands on it.
Okay.
I'm aware of what it is.
Okay.
You guys. So I work for AWS.
Ah, okay. Yeah, cool. Good. So, in the previous talk, this particular outage, the world's worst security outage, was mentioned. This was almost a year ago when let's say a flaw in a security tool caused a kernel bug which hit computers worldwide. I was traveling by plane that day. I didn't take this photo, but I saw very similar screens. So one of the things that we can do with eBPF is create security tools that are not subject to this kind of kernel crashing problem. I'm Liz Rice. I work at Isovalent, which got acquired by Cisco just over a year ago. We, members of my team, were co-creators of eBPF itself. We also originally created the Cilium project, which is now the de facto solution for Kubernetes networking and is owned by the CNCF. I've been involved with the CNCF for many years now. And the CNCF is probably best known for being the organisation that, owns Kubernetes. Come on in.
Okay. Hello.
All right. So I shall just carry on because I know we're under a bit of time pressure. So Kubernetes is really becoming the platform of choice for many, many workloads these days. I think it's probably best known, most commonly used for new applications where there's microservices architecture, containerized applications being deployed. We might call those modern applications. But we're increasingly seeing it also used for AI workloads because of Kubernetes' ability to scale. It's really suitable for AI workloads. And we're increasingly seeing people running workloads that were originally designed to run on virtual machines, but they're now being moved to run in Kubernetes platforms. And those could be running on-premise, on bare metal. They could be running in the public cloud. They could very well be hybrid cloud or multi-cloud. And the challenge is that in these Kubernetes environments, you can no longer use IP addresses to identify different workloads. So the security and network tools that were previously used, that used IP addresses to identify each workload, that's not going to work in a Kubernetes environment. And so those teams tend to see those environments as a kind of black box, and they need different tools to map to those identities. The core of that problem is that in Kubernetes, applications run as services that are backed by some number of pods, and the number of pods will change as services need to be scaled up and down in response to demand. Every pod has its own IP address. And because those pods can be created and destroyed, those IP addresses get used and reused, and they may be reused for different applications. So we can't use the IP or ports as a service identifier anymore. So the tools that are using IP addresses to identify workloads are no longer appropriate. I grabbed this picture. It has Python on all those tools. That was entirely accidental. I meant no shame on Python. That was just a coincidence. So I'm going to come to what is eBPF? eBPF is a technology in the kernel that makes the kernel programmable. It allows us to load programs into the kernel and change the way the kernel behaves dynamically. As application developers, we typically think of applications that run in user space, but when they want to do anything that interfaces with really hardware. So accessing files, sending or receiving network messages, allocating memory. Applications have to ask the kernel to do those operations on their behalf, and they do that through this system call interface. The kernel is also coordinating multiple different user space applications that might be running at the same time, and it's checking for permissions. Now, with eBPF, we can load programs dynamically into the kernel, attach them to events, which could be different kernel functions, could be a packet arriving at a different point in the network stack. And those events trigger the eBPF program to run. And the interesting thing is that accessing files and networking and memory and changing privileges and checking permissions and starting new processes, all of those events are interesting for security purposes. And we can attach eBPF programs to all those kind of events. We also have the advantage of what's called the verifier. So if you were at the talk a couple of talks ago in here about formal verification, it was talking about how you can guarantee, well, safety or security of a program. The verifier analyzes a program as it's loaded into the kernel, checks every possible path through that program, and verifies that it's safe to run, that it can't dereference null pointers, that it won't access unsafe memory. This is how eBPF programs are going to avoid the kind of kernel crashes that I showed a photo of earlier in the talk, for those of you who were a few minutes after I started. So let's think about how, before I move on to eBPF and Kubernetes, I want to show you a little demo. So I've got a very simple eBPF program here. This is the eBPF code here. It's defined as a string in this Python code. I'm going to attach it to the system call openat. Openat is called whenever we open a file. And all it's going to do is get the name of the currently running command, which is the name of the executable that made this openat call. And I'm going to trace out the file name as well. And then I've got some Python code here that does the compiling and loading that program into the kernel. So I need to run that as a privileged user. And whatever operations whatever I do that opens a file is going to cause some tracing to be generated. So, for example, I've got a file here. It's traced it out here. But you also saw a whole load of other tracing happening because when I ran the cat executable, it actually accesses a whole load of other files as well while it's doing it. You can also see here, just by coincidence, systemd happened to look at a file while I was running this, which makes a very good point that eBPF can see everything that's running on this machine. Okay. So in a Kubernetes environment, this is super useful because all the containers that run in all the pods on any given machine share one kernel. And whatever we're doing in those applications, we might be accessing files, sending and receiving networking messages. Whenever Kubernetes is creating containers, all of those things are happening in this one shared kernel per machine. So every host has one kernel, and that kernel can see everything that's happening across all of those applications in all of those pods. So if we can use eBPF to instrument the kernel, we'll see everything that's happening in those applications, and we don't need to make any changes to the applications themselves. We don't need to change their configuration. We don't even need to restart them. eBPF will see them automatically. And this will be really powerful for folks moving their tooling from a traditional environment and needing to get that visibility and control inside a Kubernetes environment. Because the eBPF tools have got visibility into everything about the kernel, they can see how processes relate to things like C groups, they can see how those relate to containers and pods, and we get that detailed visibility that we need. We can also mitigate vulnerabilities using eBPF. And one example I want to show you is a packet of death vulnerability in the network stack in the kernel. So the idea here is there's a particular format of packet that crashes the kernel because there's a vulnerability in the kernel that doesn't know how to handle that packet. And if I was a malicious attacker, I might craft a packet so that it deliberately crashes the machine. With eBPF, we can hook into the network stack, we can inspect the individual network packets, and we can decide, oh, this is a packet of death, I'm going to discard that packet. And then that avoids the kernel crashing. We've been able to load that program dynamically, so we can dynamically prevent that vulnerability from crashing the machine without having to roll out a patch, without having to reboot the machine. I'm going to show a little demonstration of this. Again, I've got another simple BPF program. This is essentially saying, it's looking at a packet. I've got a function that says, is it a ping packet? And at the moment, all I'm going to do if I find a ping packet is make a trace, make a line of trace. So in this window, I'm just going to start pinging locally. So this is my local host pinging locally. And you can see the sequence numbers ticking up in the bottom half of the screen. Then I'm going to run my program. No, it's called ping. Okay. And we can see trace lines showing the ping packets. Great. Now, I'm leaving that ping running, and I'm going to change the program. I'm going to say, if you see a ping packet, drop it. So I'm going to rerun the program. We'll still see the tracing in the top half of the screen because we're still sending ping packets, or the eBPF program sees those ping packets, tells the kernel to discard it with that drop return code. And in the bottom half of the screen, you can see the sequence numbers have stopped ticking up. So we're discarding those packets. And I can change it back again. And rerun the program. And you can see in the bottom half, the pings are starting to go through again. So we dynamically changed the way that the kernel's network stack was behaving. So it's something like that. If it's a ping packet, drop it. Obviously, ping is not a packet of death. Ping is perfectly legitimate. But it's just to illustrate the idea that we can dynamically change behavior. And in particular, we can mitigate vulnerabilities on the fly like this. Now, so far, I've shown some eBPF code. Not everybody wants to write eBPF programs themselves. It's kind of quite quickly becomes kernel programming. So rather than you writing eBPF programs, you can use a project called Tetragon, which is a sub-project of Cilium, and that provides you a higher level abstraction for security purposes. So Tetragon, very high performance, gives you a way of hooking into lots of different types of events, whether they're process executions, accessing files, privilege escalations, network messages, all these kind of things that we can hook into with Tetragon. And we can either report on them and send the information to a logging system or generate metrics. Or we can even, as I'll show you shortly, we can enforce, we can block these malicious activities. Tetragon's also Kubernetes aware, so it can correlate activities to the applications and the pods and the namespaces and so on where those activities are happening. Why did we call it Tetragon? So you probably noticed that the kind of mascot for eBPF is a bee. There is a particular type of bee called a tetragonistic bee that is, it's a small bee, it builds unobtrusive nests, it generates lots of honey, and it's generally considered to be harmless for humans. So all those characteristics seem like a nice kind of bee to represent the Tetragon project. By default, Tetragon is going to generate an event every time a process starts and stops. So I'm going to show you that. So I meant to mention, I'm going to show you Tetragon just running on a virtual machine. It can run on Kubernetes. It could run in either environment. So it's just really to keep things simple. I've just got it on a virtual machine. And I've actually got it running as a Docker container. And I also have this alias to make it easy for me to run commands inside that Tetragon container. So when I type DT, just think I'm sending a command to Tetragon. And I can get events generated in a nice, compact, human-readable form. And then whenever I run something on this machine, or whenever anything runs something on this machine, we'll see process entry and exits. We may well see some process entry and exits happening from some other processes that happen to be running on this virtual machine. So whatever I run, we'll see the process entry and exit by default. Now, that human-readable output represents a more complex JSON output for each event. And the JSON information is going to tell us what the executable was, when it was run, who ran it, where it was running, and what directory it was running in. We get some unique IDs to identify that process. We also trace out the parent process, and then we can use multiple of these events to build process hierarchies. So we can correlate the parent to the next parent to the next parent. So we can see the whole history of what caused something to be executed. And you might send those JSON events to a database or a SIM or what have you. If we were running in Kubernetes, that JSON event information would have rich information around what pod was running in, what container, what namespace, what node, what the workload was, and so on. Okay, so by default, process entry and exit. Everything else requires us to load a policy to describe what events we want to log out. So let's say I want to alert on access to a file or a set of sensitive files. And for the sake of demonstration, I've got a policy, a pretty simple policy that's going to look whenever the kernel checks permissions on a file, which it does whenever you access a file, and I'm only interested if I'm accessing this temp.lis file. So I'm going to load that policy. I've actually already got the policy. TP stands for tracing policy. I've already got it loaded, and I'm just going to enable it. It's called example. And then I'll start looking at events again. And if I look at a file, well, let's start by looking at that sensitive file. And we get the process entry, the process exit, but also 2 read events showing us that there were 2 attempts to read from that file. If I looked at some other file, I've got another text file here. We only see the entry and exit events. We don't see read events. So we can be very granular about exactly what events we're interested in. And the important thing is where we're filtering or where we're making those decisions that events are interesting. There have been security tooling using eBPF for quite a while. And the sort of first generation of these tools would gather events, say, for example, every file open event, pass those events to user space where they get compared against a policy. And then if it turns out to be a malicious event because it matches the policy, then you'd generate logs or alerts or what have you. With Tetragon, we actually do that filtering in the kernel. So we can check, in my example, is the file name /temp/Liz? If it is, that's when I generate the event. So we've got a much, much smaller amount of event information being generated, which makes it considerably higher performance. It also means you're not having to wade through lots of logs if you log all of the events. People quite often ask, well, okay, what is the overhead? What is the performance? It obviously depends what you're measuring, what your policy is, and what activities are happening on your system. But a couple of benchmarks that we put together. One is tracking process execution. The benchmark we used for this was actually compiling the Linux kernel, which results in a lot of process execution events. And it was less than 2% overhead to track those events. Another example was a benchmark that we put together for file reads. Again, well, actually considerably less than 1% CPU overhead as a result of those policies. So they're very affordable in terms of the overhead that you might get for a given security policy. I mentioned we can also enforce these policies, so we can stop these events from happening. So let me show you that. I have a policy here that's very similar to the policy I just looked at. So it's still looking at temp Liz, but this time, if the event matches the policy, I'm going to kill the process with a kill signal. So I'm going to disable the previous policy and enable that enforcement policy and log out the events again. Let's clear the screen. Okay. So if I look at a non-sensitive file, we'll see the process entry and exit like before. That's what we expected. Now what happens if I try and look at the contents of that temp Liz file? Gets killed. So we can see, well, first of all, the end result here. I didn't see the contents of the file. I just see that the process was killed. And in the events that were output, we see the process started. It attempted a read. Remember before there were 2 reads? This time there's only one because that read triggered the kill. So it killed the process. In the kind of, let's say, traditional approach that I was showing with the sort of previous generation of eBPF-based tools, let's suppose we have a compromised application and it makes an attempt to do something malicious, like opening a sensitive file. And the kernel performs that action, but maybe there is tooling, an eBPF tool, that detects that action's happened, passes it to user space, gets compared with a policy. We determine that the event matches the policy and is something we don't want to have happen. So user space could kill the kernel, kill the process via the kernel. So it sends the sig kill to terminate that process. The problem is there is a period of time after the bad action completes, so after we've opened the file and before that process got killed, during which we don't know what's happening. Data could have been read out of the file. We can't tell. We don't know how long it's going to take to report or to kill that process. With Tetragon, because we can compare it in the kernel. We can determine whether we think this event is malicious or not in the kernel. And we can send that signal directly and synchronously from the kernel to kill the process before it had a chance to make the out-of-policy event. We still want to report that event to user space, but the actual thing that we wanted to prevent never happens. The thing that we believe was malicious never happens. So we've prevented the possibility of, for example, data exfiltration. It also avoids that kind of just the performance overhead of transitioning from kernel to user space. So very quickly, wrapping up with a few more use cases of the kind of policies that we can enforce with Tetragon. I just showed you sensitive file access, but you might want to understand, okay, what was the process that performed that operation? Was it running in Kubernetes? Which pod? In which namespace? Did that process have privileges? Was it running as root? I've got here a couple of screenshots from integrating the Tetragon output into some Splunk dashboards, just to sort of give some ideas there. We can also enforce network policies. So you might want to prevent TCP connections or messages being sent and received to and from certain destinations or sources. Or we can track, generate event information about when that data, when those messages were sent and how much of it. We can have policies that look at what privileges different processes are running under and understand whether there are pods running with elevated privileges and why. Have processes escalated their privileges or changed their capabilities. We can limit the executables that can run. So we can say, if I try to start a new executable, is it an approved executable? We can look at the security of the host on which these are running. Is there something trying to change the kernel by loading or unloading kernel modules? We can use eBPF to check whether kernel modules are signed or not. And then I talked about network, the amount of network traffic. You might want to know whether an amount of traffic in a given period of time exceeds a threshold that suggests that maybe data has been exfiltrated. And if we see some suspicious network traffic, being able to understand what was the process that caused that to happen, and which is the team, who owns this workload, what namespace is it running in? This is the kind of question you might want to be able to answer that Tetragon can help you with. And then finally, the idea of mitigating CVEs in devices. So my dream is that one day all Linux-powered devices will have Tetragon running in them to mitigate CVEs dynamically. You can load these policies and never again be vulnerable to, well, the vulnerability would still exist, but it would be mitigated by eBPF and by Tetragon policies. I've said Linux. There is eBPF support for Windows coming. I've seen some pretty good demos. It's on GitHub, Microsoft, eBPF for Windows. But also what's happening is this idea of protecting devices and having this kind of live CVE mitigation. And Cisco, who acquired Isovalent, one of the things they are doing with that technology is dynamic CVE mitigation for switches. So you don't have to reboot switches if they have this CVE mitigation capability. If there's a vulnerability, you can plan when you want to do those patches rather than having to do them as an emergency. So hopefully we will never have to see sites like that again. All right. I hope that this talk has given you an idea why eBPF is so powerful, why it's so important for eBPF, for security instrumentation, and how we can use it in Kubernetes environments and in non-Kubernetes environments for detecting and preventing malicious behavior, as well as mitigating CVEs. If you want to learn more, there are some books you can download from our website. There's also some real-time labs. So isovalent.com/labs has a number of sandbox environments where you can play with Tetragon and some of our other technologies. Pretty much run up to time. Thank you very much for being in my talk.